Okay, hello everybody. Welcome to my presentation about space geodesy and overview. Today I'm going to discuss about the meaning of the space geodesy and the space geodesy methods that we use actually. And later I will explain some of my research that I have done with my students. So let me go back to the definition of geodesy. Geodesy is science and techniques of determining the Earth's geometric shape, orientation in space, and gravity field. Today, when we talk about geodesy, people just look at the first part of this definition, which is related to the science and technique, measuring or determining the geometric shape of the Earth. And these people, they don't know about the other definitions of geodesy, just determining orientation of the Earth in the space, which is related actually to defining the reference system. Also the beauty of geodesy, and also the gravity field of the Earth. So if we did consider this as a definition for geodesy, what will be the space geodesy? So when we do geodesy using a space measurement, that's called space geodesy. So these are some methods that we use in a space geodesy. Global navigation satellite systems, you know it very well. Yes, GLONASS and other systems, position systems. Satellite laser ranging, lunar laser ranging, very long baseline interferometry, Doppler orbitography and radio positioning, or DORIS, satellite altimetry, interferometric synthetic radar aperture, and global navigation satellite systems, reflectometry, and at the end, the satellite gravimetry. I will try to explain these things shortly during this lecture. But before that, I want to emphasize that space geodesy is a broader concept than satellite geodesy. In fact, satellite geodesy is a part of a space geodesy. The differences are related to the measurement scope, data collection, instrumentation, and applications. They have different goals. For example, when you use GNSS, your focus are mainly for the measuring and the techniques of measuring the Earth. So this is the satellite. This is satellite geodesy. You use mainly artificial satellites, but in a space geodesy, we go beyond, much wider. Let me explain this in the next step. So, in global or GNSS system, we have some points on the ground, as you see on the figure, and the coordinates of this point have been already determined precisely. But how? The other techniques that I will discuss this later. So from this point, the coordinates are injected to the satellites, and the satellites will return the coordinate down to the users. And in that way, it is like that you are interpolating the positions. It's like an interpolation. You give some point, you give the coordinate to satellites, and the satellites move and distribute the coordinates to the users. And based on some measurements, of course, between satellites and receiver, you will transfer the coordinates from the satellites, which are known points, to the unknown points on the ground. The measurements, I think you all know about this. GNSS system is very well known with code, carrier phase, and Doppler shift, and others. There are other measurement types actually. But the main purpose or application, I would say, it's the positioning actually, absolute, relative, real-time, network RTK, kinematic, pneumatic orbit determination, navigation. They are all position aspects of the GNSS. Also, deformation monitoring. Deformation monitoring is also a part of position, but it's more It's also more engineering side, actually, monitoring displacement. And GNSS meteorology is studying the atmosphere of the GNSS. And reflectometry, it means that when the satellites, GNSS satellite send the signals to the ground, and the signals are reflected back, are reflected from the ground, and then we can measure these reflections and study different parameters, like can study atmosphere, we can atmosphere or sea level variation that will come later. So for meteorology, always we in positioning, we always think that they say that okay, the ionosphere or troposphere are actually the disturbances. And then the point is, goes to that this atmosphere is just get some reflections and get some problems. And then in positioning, our goal is to be in the position precisely, actually. And we try to. So I was telling that when the satellites send the signals to the receivers, and always we think that the ionosphere or troposphere are disturbances. They are limiting the accuracy of the positions or the measurements. But we can do it in the opposite way. We can assume that the data, the coordinates of the points at the ground are now, and the satellite positions are now, and we want to see what is happening to the signal or the measurements, and how the atmosphere can affect them. In that way, we can do the inverse problem and to determine, for example, the total electron content inside the ionosphere, or also model the troposphere. Radio occultation is another technique which is used in GNSS. So you see that this higher orbiting satellite sends a signal to a lower orbiting satellite, and when they are outside the atmosphere, this is in a straight line. And after a while, when the satellite moves, in some position, you see that the signal goes through the atmosphere and refracted. And based on that refraction, we can make some profiles of cut atmosphere as like profiles and measure what is happening inside the atmosphere. It's the technique that has been used in CHAMP mission, GRACE mission, TRASAR, and COSMIC 1 and 2 R2 satellite missions dedicated for this mission, actually. It's called GNSS radio occultation. And reflectometry, as I already explained, the signals from the satellites are continuously go down to the ground, and they are reflected back to their space. So the problem is that this signal is too weak, and it's not easy to measure. But if we can study what is happening inside this land or ocean surface of land or ocean to see what is happening there. For example, here I have let me see if I can draw the laser pointer. So you see that these are the double antenna. One is upward, one is downward. The downward one is for getting the refraction. Actually, here I have done for the ocean as a tide. This is used as a tide gauge. For example, on the right-hand side, you will see this is the real case of the GNSS tide gauge, actually, which is at the Onsala Space Observatory of Chalmers University, actually, in Sweden. As you see, there is an antenna upward in that position to get the coordinate, and the one is downward, actually, so that to get a reflection. And in that way, they can, just by measuring the reflection of the signals, GNSS signals from water, they can measure the sea level change. Also, it can be done in that way that we have some satellites, they have some special instrument inside so that they can receive the reflection, actually, from the ground. And even over the ocean, we have always problems with modeling ionosphere over the ocean. So in that way, if we can get the reflection by satellites, we can model this model the sea level and study sea level much. These are called Geodesy reflectometry, which is a rather hot subject these days. And a future focus on will be on that. We have many satellites, as you see in that image here. The many satellites all around the Earth are moving, and in the future, we will be able to use all of the satellites for positioning. So much more redundancy than we have now. Therefore, we can measure, we can determine the better ionospheric and tropospheric models, especially over the ocean area, so which is very hard. We do not have some receivers there. Then we have to use the Geodesy reflectometry. The quality of navigation will be better, and also we can do radio occultation for better modeling the atmosphere. Another technique is satellite laser ranging. So it's that with the lasers from laser stations, a satellite is, the satellites are like a ball, and they have reflectors on it, some prisms, and they will send back any laser beams that this is shoot from the ground to them. And since the speed of light is known, the travel time is determined when the signal is the laser start to travel to the satellites, and come back, the time is measured. So based on this time, measuring the time and the speed of the laser, we can determine the distance from the satellite and this SLR station. So as you see, one side of this measurement, which here I can call it D, we have satellite. The other side, we have the station. And the changes of this distance depends on the changes of the position of the satellite and position of the or position of the station. So by studying the changes in this, we can do many studies. Here, for example, we can use this laser ranging technique for orbit determination. How is it done? In these days, we have satellites that they have reflectors under them, so that we can use this technique to measure their position precisely, or as an extra observation to the other types of techniques that are used for determining the coordinate. Can determine Earth's rotation and length of day as the definition of the terrestrial reference frames, cluster deformation, monitoring, of course, monitoring of the points that this laser ranging station are at, and calibration of the other satellite-based methods like altimetry, for example, and gravity field determination, which mainly related to the perturbation of the satellites. On the right side, you will see a station, SLR station, which is in GFZ Potsdam, is active. This, you see that this is there's a like a gun here. It's a telescope here for shooting the lasers. So lunar laser ranging is very similar. They have put more than three reflectors, about three now are the Apollo reflectors, Apollo 14, 15, and 11. And you see the photo of the reflectors here. And they have put these reflectors on the surface of the moon. Also, L21 is also another reflector this is from French, I think, French Space Agency. And this one, L1, it's not working. It seems that when the spacecraft wanted to move back, make a lot of dust, and this reflector is not working. But what is measured? If we have a LLR station here, we just find with laser, we can measure the distance between the satellite, between this reflector at the surface of the moon and the station. And what is the point here? You see, it's a barycenter, center of the solar system, and the position of the Earth in the solar system and position of the Moon in the solar system is known. They are rather stable. And as you see, by measuring the distance between the Moon and between this reflector and the station there, we can determine either the position of the reflectors, and by that, if we consider that the points on the ground are fixed, then we can measure the changes in the Moon, libration of the Moon, movement of the Moon, determining orbit of the Moon. These are the things that we can study. Or the opposite, if that one is fixed, we can measure what is happening inside the surface of the Earth. Both are possible. And here you will see some stations actually in the world that they do LRR. And there are not too many, there are few. But they are active, they are working. So mainly this LRR technique is for the measuring for measurement of the Earth-Moon distances, for determining coordinate system between Earth and Moon, or some dynamics of the Earth and Moon system. The Moon is very important actually, because it affects the climate. The Moon has the effect on the tides and also many other things that happen. So it is very important to measure this, to have control on the Moon system actually. Orbit of the Moon can be measured, as I explained, libration. So it means that some movements up inside the Moon, and general relativity theory can be tested by that. You see that if this the bending of the signals due to the gravity field are really that big, how big are they? Are they in agreement with the theory or not? And also determining the shape and the size of the Moon, of course. In VLBI, we have very long baseline interferometry. The principle is that there are some celestial objects that they sense that there's some constant frequencies, constant or stable frequencies down to the, and with some radio telescopes, we can measure actually these signals. And for example, if we have one quasar, but since they are very far from the Earth, they are very far from the Earth, we can assume that they are parallel, they are two parallel. So when the signal comes to the one station, and the same signal comes to another station, but they are not coming to in the same time because of the distance of the stations. So then here we have a little bit extra distance or extra time delay that we have. The delay between receiving the signal from one station to another. Based on that delay, we can determine this baseline, the distance between them. Mathematically, generally it's very simple, but this principle is very simple, but in reality, the mathematical model is not that simple because there are many corrections that you have to consider. For example, most important one is the correction to atmosphere. So then this is the baseline vector, and this S is a unit vector pointing to the quasar. And if we do this inner product of that, then we can determine the time delay. But in reality, this is the time delay which is measured precisely by atomic clocks. And the point, it is the coordinates of the celestial object is now. We know the position of the quasars, and then we determine the baseline between the stations or radio telescopes. It means that in a very long baseline interferometry, we measure the relative coordinates between the radio telescope antennas. On the left, you see the VLBI stations, which are active now in the world. You just see the positions. On the right, you see the one which is on Solar Space Observatory in Sweden. They open sometimes that people can go there to visit them. I have been there. Onsala is here. There are two relatively new radio telescopes there, and this one is rather old. The diameters are around, I think it's 7, I don't remember, 13 meters, something like that. For these two, this one is larger, actually. And what is the point for that? Again, as orientation, as you remember, the definition of geodesy is as orientation, and rotation is one of the goals of geodesy. Reference frames, of course, improving the coordinate, crustal deformation, and plate tectonics, of course, because this variable stations are under some tectonic plates. And then we can measure the relative distance, then precisely, then we can see to which direction the movement, the plate is moving. Well, as an application in astronomy and definition of celestial reference frame, which is very important, of course, in satellite geodesy, and combining VLBA with other type of measurement for atmospheric studies. If you remember from in the beginning of the presentation, I said that we have some noun coordinate on the ground, and these coordinates are injected. These coordinates are transferred to the coordinate to the satellite, are used for determining the coordinates of the satellites. And these coordinates, actually ground, are determined based on other space geodetic technique. That VLBI is one of them, and one of the precise. You can determine distances up to 1,000 kilometers with up to millimeter accuracy, something like that. Doppler orbitography and radio positioning is very similar principle like Doppler positioning or transit system. Then we have a source sending a signal, and the source is getting closer to us, the frequency gets higher, increases, and when it gets far from us, the frequency reduces. That's what we know. But in Doris system, it is a little bit different because the source is constant at the ground, on the earth. You see these antennas down on the ground, these are constant, they are not moving, but it's the satellite which is moving. The satellite is moving, and when it gets closer to the head, which is called beacons, to the beacons, and the frequencies are increasing. And when they go far from that, and then we go it. And this frequency difference, which is called Doppler shift, actually, is measured, and based on this Doppler shift, you measure the Doppler shift, you can observe the frequency, and you have to observe this Doppler shift here, and this is F is the transmitted frequency that from the beacon. We can send it to the satellite with the antenna send it back. And here you see that we have velocity, and it is inner product of velocity and the unit vector from beacon to the satellite. The coordinates of the satellite are here. So these are the related to the coordinates. So if we measure the coordinate, these Doppler shifts, based on these measurements, and also we have coordinates of the beacons, we can determine the coordinates. And today there are many satellites, especially automated satellites, that I could with Doris antenna, Doris system antenna. So their orbits are determined precisely with this system. Ultimately, principle is very simple. The signal radar signal comes to the sea surface and reflected back. And based on measuring the time and travel time and the speed of the signal, you can determine the but there are many other, again, corrections here that we have to consider. And one is that actually, the big one, atmosphere. What we measure here is the sea surface height. This distance is measured, but since we have the coordinates of the satellite, we can determine the height of sea from the reference ellipsoid. But however, we know that this sea surface is not actually, does not coincide with the geoid. And they have a small difference, which is called surface topography. But this is important because surface topography will show that in which direction the water moves. So we can determine how the water movement of the water over ocean if we have a precise geoid model from another source, for example, satellite gravimetry, and we measure the heights, sea surface heights. And in that case, by subtracting these two and taking derivative, for example, towards north and towards east, we can see how the water moves. Or we can measure the geostrophic currents, and also we can determine eddy currents out of that for oceanographic purposes. So ocean has a significant actually role in climate these days. So it's very important. So this satellite altimetry play an important role actually in that business. Geoid determination, you can use, of course, this measurements of the sea surface topography to determine a geoid model. Also, satellite altimetry can be used for over the lakes or over big rivers too, as long as they have water and the satellite actually radar beam is that the size of that is that much that you can get the reflection from the. That's good. Then we can have, and also with hydrology and water resources and coastal zone monitoring, because you know that these coastal zones are changing all the time, especially these days based on this ice melting, the water goes up, the sea level rise, and the shape of the coast is not constant. Also, there are some other factors of erosion and other things that can be monitored by satellite altimetry. I think INSAR is now very popular. INSAR is also another space geodetic technique, and it's used actually similar principle like VLBI. But in that case, the object is not that far so that we can consider like quasar in infinity and we consider the lines coming to the Earth parallel. They are not that far. Therefore, we have such a triangle like this here. And it's called aperture. Aperture, you know, is like a camera diaphragm that when it's just direct relation with the angular resolution or quality of the. If we want to measure the high quality, some high quality data, for example, for measuring height, then we need to have a big antenna here. Big antenna here to measure it, but in reality, it's not possible to have, for example, an antenna with large 1 kilometer diameter is too big. But instead, we can synthetically make it like that. So step by step, when this sending source, the radar, so it's moving, and for each point, point by point is up to this point, it will create synthetically and a big antenna for it. It can be used for determining the topography, or it can be used for determining the deformation, and if we can measure this phase difference. I think this is a very popular subject now. This is between remote radar, remote sensing, and also between geodesies. Probably you have seen these things before. If this is the phase before the formation, this is the phase after the formation. By looking at the phase, you cannot see that much. But when you subtract them from each other, then you will see some fringes, so showing some features of the land surface. So I'm not going to go to the details about this. I think it's very known. And satellite gravimetry, which is actually my field of expertise, it's working like that. If you have a satellite moving around the Earth, this orbit of the satellite is not very smooth. This is because of different perturbing forces that act the satellite. These forces can be of gravitational or non-gravitational nature, and the gravity field play the main role here. So the point is that if I can measure the orbit of this satellite, or I have some instrument or sensor to measuring some gravitational parameters, I should be able to determine the gravity field of the Earth. The first thing which is important actually for any space or satellite geodesy or satellite gravity is the orbit. This orbit, as you see in the figure, can be determined from the ground stations, like for example SRR, DORIS system that I already explained, even with higher orbiters like GNSS system. They all can be used for determining a precise coordinate for the satellite, because these changes of the satellite movements is due to the gravity field, of course the biggest one. This type of determining the orbit is called kinematic orbit determination. So if I have the gravity field of the Earth already, if I have the mathematical models of the non-gravitational perturbation, and I have some other mathematical models, if I consider them with a known gravity field, I can generate the orbit. For example, when you use GNSS satellite, for example, you want to design your plan for measurement for another day, you will use the broadcast FM almanac data. Almanac data, or this is the predicted orbit, is actually determined based on this principle. They use the gravity field, these forces, and generate the orbit. This type of method for orbit determination is called dynamic orbit determination. And when we combine them, it goes kinematic. So orbit is the first thing actually which has first measure, I would say, for modeling the gravity field for a long time. Another technique is to use an instrument which is called gradiometer. In gradiometer, there are 6 accelerometers which are 2x2 parallel and 2x2 orthogonal, like a coordinate system that has a distance of about, for example, for ghost mission 2 meters. So they can measure the changes between the accelerometers here and the accelerometer back, front and back, up and down. In that way, they can measure the second order derivative of the gravitational potential. So in that case, they can measure higher frequencies, or better, the changes of the high frequencies of the gravity, or changes of the gravity field of the Earth. Consider that derivative mathematically is an amplifier. So if you want to amplify a function, you have to take the derivatives. When you take first derivative, you will amplify it a little bit, second a little more, third, and fourth more. So up to now, we have second order derivatives actually, which goes satellite gravity actually. Yeah. Another technique is that we have 2 satellites following each other in an orbit, and then the distance between the satellites are measured precisely. In addition to GNSS satellites, and also we have some stations here. If we have reflectors under the satellites, we can measure the coordinates of the satellite more precisely, actually, with even the DORIS system. So it has the main, this is a technique which is used in GRACE mission and GRACE flow mission for gravity field modeling and the changes of the gravity field, even for earthquake assessment. So range rate and the line of sight measurement are the 2 sorts of measurements. There are mathematical formula for that. This is big, and I don't want to go to it. Just know that this distance, which can be measured, and when the satellite moves around the Earth, this distance changes. And by measuring these changes, we can determine the gravity field. So what are the applications? Orbit integration and prediction. So you can, of course, the product of the gravity, the satellite gravity, which are the gravity models, are used for orbit determination or orbit integration. You can determine the gravity field locally as well. not only global. You can study crustal structure, lithospheric stress, mantle viscosity, post-glacial rebound, and groundwater storage, earthquake, ocean bathymetry, and sediment, and many other things that you can do with this satellite gravimetry. But some of them that I have studied so far, for satellite, generally in space geodesy, not only satellite gravimetry, are here, which I explain them one by one, very shortly. Before that, let me explain what is crustal structure. Well, we know that there is an isostasy theory that they say that the mountains have roots inside the lithosphere, so inside the upper mantle. So Airy was a guy who assumed that these mountains are like columns, and the one which is taller or larger goes through the mantle more. Pratt said that no, they are not the same. They are not this. They have not the constant density, and they are not like that. Say they have different densities, but they all go through the mantle at the same level. But when they say there is none of them, because you cannot assume that the crust is like a columns. And also when you have shear stress between these columns that you cannot ignore this. Therefore, he come with an idea like that the compensation, that much that the mountain go through the upper mantle, they are more regional and smoother than them. So based on this principle, we can determine MOHO, which is actually the surface between the crust and upper mantle, glacial isostatic adjustment, elastic system, stress, and I will come to that later. So even mantle convection can be, and tectonic can be studied by this space geodesy. From the right side, you see this, the movement of the plates, as I already explained. You have here I have the GNSS as an example. For example, you have receivers on the plates, and the coordinates are determined precisely. But not only with GNSS, we have SRR, we have VLBI, we have LLR, we have many other satellite techniques that they can measure the tectonic movements. Also, in these tectonic movements, which you hear, there are also results from they show or reflects on mantle convection pattern on them. Also, with satellite gravimetry, we can study the mantle convection, what is happening inside this. So mantle convection, you know, they get warm, there's material, they go up and get cold and come down. There's some circulations inside that, which can be studied by studying the gravity data, but not directly with this GNSS. So it was supervision of Matlub Hussein. He was with me a couple of years ago for doing his PhD. And then we have focused on isostasy and determining MOHO from satellite gravimetry methods. Also, we have studied about with the gray state or the Kashmir earthquakes, actually. So I just give you one example of what we have done. That. So here you see the left side is the Himalaya, as you see. We have used the GHOST data, which is a satellite graduometric mission, and we determined the MOHO depth under that area. And on the right-hand side, you see the density contrast between the crust and mantle that we have determined using GHOST gradients. But of course, I should add that we have also used seismic data for it. And this is not only with satellite gravimetry. Satellite gravimetry or satellite, it comes with as a complement to other data for study. Here you see another study for the determining the Eulerian pole, actually, that any movement at the surface of the sphere is a rotation. So, and the center of this rotation is called Eulerian pole. And here you see in Iran, it's Iran, that we have some velocity we determine by GPS system, by GPS. And these rotations are actually around a circle, along a circle. And the center of the circle is pole. And in this article with this guy, when I was at Geodesy University, it wasn't too much sine and cosine in the formula, and then lots of ambiguities in the solution, and we try to derive a linear model for that. And yeah, you see the result, much faster and much more efficient. Also, I spoke about the gravity, the tectonic movements. Here, we try to combine, actually. I use satellite gradiometry data, goes here to measure the mantle and the stress below the crust, below the lithosphere, sorry. And I asked Bernard Steinbergen, with my colleague at GFZ, and he used the GPS data actually for mantle convection, and we combined these two data to come to this stress model on the South American. As you see here, is on the mountains that which are very active in earthquake, and you see the highest stress in the snow response. That just should be. And Nazca plate and South American plate are moving towards each other. There's some interaction, some what is called intersection with each other. It's also another study that we used GRACE-4 data. GRACE-4 for monitoring an earthquake in Iran. Here you see the point, yes, this is the point that the earthquake happens, the epicenter point of that earthquake. And this is the tensor of stress tensor that we have determined from the GRACE-4 data. So how we do that? We have some gravity field before the earthquake and gravity field after the earthquake. And we computed the stress from the bottom of, propagated from the bottom of the lithosphere and to the lithosphere at the epicenter level, and then subtracted them from each other to see what is happening. So now you see that this vertical stress is exactly at the point, and you see this point, you see here this tensor has negative value here, stress has negative, and also some shear. This is another way of doing it. Another thing which studied by satellite is elastic thickness. What is that? If it is a lithosphere, the thicker the lithosphere is, the less bending do we have. So if we have load here, and the lithosphere is thinner, it will bend more than it is thicker. That's the principle. I use this idea for the flexure theory based on this, which is related to the bending of the base under the loads. With gravimetric movement, I assume that they are equal, and based on that, I come with an idea and develop a theory for this idea, and it worked for South America. And later, when I was working with that idea, Martin Pituna was with me as a guest, and I developed this theory for the satellite data, and he applied it over Africa. And here you see that the large, here is it elastic thickness is here is large. It means that the lithosphere is the thickness is higher here. Well, not the lithosphere thickness, the effective elastic thickness. And so if we assume that the lithosphere is elastic, then it will be taken like that. Also, post-glacial rebound, we know the mantle is viscous. And when we have lithosphere and mantle and load, bend them, then the lithosphere down toward the mantle. But what happens if the load goes? So when they go away, the mantle push upward the lithosphere. Then it's called glacial isostatic adjustment. And I have done this actually, published in my book. Actually, this is the changes of the geoid during the GRACE time. GRACE was 15 years of measuring the gravity field in Wolf and Scandia, because here to 20,000 years ago, there was a big ice cap which has pushed down the lithosphere down to the upper mantle. But now the ice is gone, and the mantle is pushing upward the lithosphere with very slow rate. And this is what we see with the geoid. And if I had to change it to the height of the lithosphere, mathematical models are already there. I have written them. And you see that it is like that. I have compared this with the GPS data that they have measured this land uplift. It has very good agreement. This is another application. Also, GRACE and GRACE4 can be used for monitoring water overdose. And so here you see the global map of how the water changes, actually, the terrestrial. What GRACE shows us is the equivalent water or terrestrial water storage. But if we remove the soil moisture, canopy water or snow water equivalent, we can see how the groundwater is moving, which is very important, actually. And here you see Scandinavia and Hudson Bay in Canada, they are big, but it is because that we have not considered post-glacial rebound over this area. So these areas cannot be that big. It could be because of that. But we can measure groundwater movements by satellite gravity. It is a PhD thesis of my student, Farzam, and Canada, and our school co-supervisor. And we worked actually on this subject for downscaling the GRACE data. It means that GRACE data are monthly, but if you want to have daily data and with higher resolution, what should we do? The point was that we should have to combine it with some other source of data, or for example, hydrological data, then we have done it. But how? It was a spectral downscaling method that we worked on that. Also, I said that everywhere we have mountains, then we have roots. But over FR area, the root is not that deep that we expected. It's because there is another mechanism actually there. This is called mantle plume rising. So it keeps these mountains more balanced. It will somehow violate isostasy theory. This is why, sorry, I wanted on the net at your institute, who was doing his PhD with me, to work on that and refine this theory to see how much the effect of this mantle plume will be on Mohovan stress, even elastic thickness. Sorry. Another study is on the net at your institute, another on the net. And the goal is to combine INSAR and GNSS data over a FR area. I think he used MVSAT data and some GPS time series. And we have done some studies for first the agreement and checking the quality of the line of sight measurements of the GNSS, and also the INSAR data, and how to combine them, how to estimate the combined velocity field for that. This is what we have done actually. The article hopefully will be published soon. And also is working now to how to use finite element method for determining the stress and strain over this area. He is still working on that. And also this is another work of one of my students that we used on GNSS networks. Actually, the idea was that they had established the GNSS monitoring network over an area which is called Lila Edet in Sweden. And there are lots of risk of subsidence in this area because of claim. And they have had this network there. And I wanted to, to work and optimize the network if we can come to the same result with less amount of data, then we can see it. And he come to that idea with the result that by removing these measurements, we can come to the same quality as we wanted for that. So measuring more data didn't improve that much. So that was the goal of optimization. Also, he did another studies, has an earthquake network in the Skåne area in Sweden, as you see here. There are some points here, but I wanted him not to just look at the quality or the precision of the data. I wanted him to go to the strain and to the final element model, and from the final element model estimate the strain error and try to optimize the network based on the strain error, not the position error. So he is concluded that if we come to these three scenarios of the optimization, he can do a good accuracy for the strainer. That was all I wanted to talk for today. Thank you very much for your attention.